We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I feel the liftoff. The clock has started. Roger. Godspeed, John Glenn.
Roger, 0G, and I feel fine.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 24 of the Space Rocket History Podcast. And now, Mercury Redstone test flights. The objectives of the Mercury Project were as follows. 1. Place a manned spacecraft in orbit around the Earth. 2. Investigate man's performance capabilities and his ability to function in the environment of space. 3. Recover the man and the spacecraft safely. After the objectives were established for the project, a number of guidelines were established to ensure that the most expedient and safest approach for the attainment of the objectives was followed. The basic guidelines that were established are as follows. 1. Existing technology and off-the-shelf equipment should be used where practical. 2. The simplest and most reliable approach to system design would be followed. 3. An existing launch vehicle would be employed to place the spacecraft into orbit. And 4. A progressive and logical test program would be conducted. First, let's consider the Mercury capsule. The principal designer was Max Faget. Unlike the Soviet spear-shaped capsule, the Mercury capsule was shaped like a cone with a cylinder on the narrow end. The blunt end was covered with a convex ablative heat shield to protect the spacecraft against the 3,000-degree heat of re-entry into the atmosphere. The heat shield was composed of an aluminum honeycomb structure covered with multiple layers of fiberglass. There was a retro pack strapped to the heat shield. The retro pack had 3 rockets that were used to slow the spacecraft for re-entry. In between the retro rockets were 3 minor rockets used for separating the spacecraft from the launch vehicle. The straps that held the package could be severed when it was no longer needed. Between the heat shield and the inner wall of the crew compartment there was a landing skirt, which was deployed by letting down the heat shield before landing. Above the heat shield came the pressurized crew compartment. This contained the astronaut strapped to his couch with the instruments in front of him and his back to the heat shield. Underneath the seat was the environmental controls, which supplied the astronaut with oxygen and heat. The system also cleaned the air from CO2, vapor and smell, as well as, on orbital flights, collected urine. The cylinder-shaped recovery compartment at the narrow end of the spacecraft contained 3 parachutes, 1 drogue to stabilize freefall, and 2 main parachutes, of which only 1 was used. The other was a reserve. On top of the recovery compartment was the antenna section, containing antennas for communications with Earth and scanners for guiding the orientation of the spacecraft. Attached to it was a flap used to ensure correct heat shield first direction during re-entry. A launch escape system was mounted to the narrow end of the spacecraft. In case of failure during the last minutes of a launch, it would fire a solid fuel rocket for a second to bring the spacecraft free of the launch vehicle so it could deploy its parachutes and land at sea. Now some dimensions. The capsule, with the cylinder mounted on top, was 2 meters, or 6 foot 10 inches long. It was 1.9 meters, or 6 foot 2.5 inches in diameter at the base. A 5.8 meter, or 19 foot 2 inch escape tower was fastened to the cylinder of the capsule. The spacecraft had 60 cubic feet of habitable volume. It was just large enough for the single crew member. It weighed about 2,464 pounds or 1,118 kilograms. Inside the capsule were 120 controls, 55 electrical switches, 30 fuses, and 35 mechanical levers. Unlike Vostok, Mercury could be rotated in 3 directions: along the longitudinal axis of the spacecraft, which is roll, from left to right as seen from the astronaut, which is yaw, and up and down as seen from the astronaut, which is pitch. Movement was created by thruster jets using peroxide as fuel. The movements and other functions of the spacecraft could be controlled in 3 ways. 1. Remotely from the ground when passing a ground station. 2. Automatically guided by its own instruments. Or 3. Manually by the astronaut, who could replace or override the 2 other methods. In his left hand, the astronaut held an abort handle that could release the launch escape system if the automatic system failed. The Mercury 7 had taken part in the development of the spacecraft, and they insisted upon the manual control as well as a window in front. The outer skin of the capsule was made of Rene 41, a nickel alloy able to withstand high temperatures. And finally, the capsule made use of the blunt body shape that, according to test, would produce the least heat upon re-entry. The launch vehicle for the first Mercury missions was a modified Redstone missile similar to what we covered in Episode 8. The modifications to the Redstone included elongation of the tank to increase fuel capacity, engine and control system simplifications, a mission abort system, an adapter section to house control equipment, and a computer to sense problems that might warrant an abort. The additions made the modified Mercury Redstone 83 feet tall, 14 feet taller than the standard Redstone. It was capable of delivering 78,000 pounds of thrust, much less than the Vostok K's 1 million pounds of thrust. And now, the Mercury Redstone test flights. We will begin with Mercury Redstone 1, also known as the 4-inch flight. Mercury Redstone 1 was the first scheduled flight of the Mercury capsule mated to the Redstone booster. The objectives of the Mercury Redstone 1 flight were to 1. Qualify the spacecraft booster combination for the Mercury Redstone mission, which included attaining a Mach number of approximately 6.0 during powered flight, a period of weightlessness of about 5 minutes, and a deceleration of approximately 11 Gs on re-entry. 2. Qualify the booster separation posigrade rockets. 3. Qualify the recovery system. And 4. Qualify the launch, tracking, and recovery phases of operation. And 5. Qualify the automatic stabilization and control system, including the reaction control system. The initial launch attempt was on November 7, 1960, but it was canceled due to a last-minute problem with the capsule. Another attempt was made on November 21st. Mercury Redstone 1's engine ignited on schedule at 9 a.m. However, it shut down immediately after liftoff from the launch pad. The rocket only rose about 4 inches before settling back onto the pad. It wobbled slightly but stayed upright, and it did not explode. Then an odd series of events took place. Immediately after the Redstone's engine shut down, the Mercury capsule's escape rocket jettisoned itself, leaving the capsule attached to the Redstone booster. The escape rocket rose to an altitude of 4,000 feet and landed about 400 yards away. 3 seconds after the escape rocket fired, the capsule deployed its drogue parachute, then deployed the main and reserve parachutes, ejecting the radio antenna fairing in the process. Meanwhile, a fully fueled, slightly dented Redstone booster and its Mercury capsule sat on the launch pad, both with full batteries and live pyrotechnics. Among these pyrotechnics were the capsule's retro rockets and the Redstone's self-destruct system, which was still active. Furthermore, the capsule's main and reserve parachutes were hanging down the side of the rocket, threatening to tip it over if they caught enough wind. Fortunately, the weather conditions were favorable, but technicians had to wait until the next morning when the flight batteries in the rocket and the capsule had run down and the Redstone's liquid oxygen had boiled off before they could work on the rocket and render it safe. In the end, all that had been launched was the escape tower. But it was an excellent test of the escape system, and the equipment performed pretty much like it was designed. It was later determined that the Redstone's engine shutdown was caused by two of its electrical cables separating in the wrong order. These cables were a control cable, which provided various control signals, and a power cable, which provided electrical power and grounding. Both cables were plugged into the rocket at the bottom edge of one of the tail fins and would separate at liftoff. The control cable was supposed to separate first, followed by the power cable. However, for this launch, the control cable was longer than expected, because they used the cable that was designed for the military version of the Redstone missile rather than the shorter cable designed for the Mercury Redstone. This control cable had been clamped to compensate for its greater length, but when the vehicle lifted off, the clamping did not work as planned, and the control cable separation was delayed, eventually occurring about 29 milliseconds after the power cable had separated. During this brief interval, the lack of an electrical ground caused 3 amps of current to flow through an electrical relay which was supposed to trigger normal engine cutoff at the end of the powered flight. This relay tripped, causing the Redstone to shut off its engine and send a normal cutoff signal to the capsule. Under normal circumstances, when the capsule received this signal during a flight, it would do two things. First, it would jettison its escape rocket, which was no longer of any use, and after the escape rocket had flown clear, the capsule would separate itself from the expended Redstone. In the case of Mercury Redstone 1, the capsule did jettison the escape rocket as it was designed, but the capsule did not separate itself from the Redstone. The capsule was designed to suspend this separation until the vehicle's acceleration had almost ceased, so that the capsule would not be hit by a still accelerating launch vehicle. This would happen when the capsule's acceleration sensors detected an acceleration approaching 0 Gs, which it would normally experience after the Redstone had shut down and was entering freefall. However, in Mercury Redstone 1's case, it was not in freefall, but rather sitting on the ground. Thus, the capsule sensors detected the effect of their own supported weight, which they read as a constant acceleration of 1 G. Because of the apparent acceleration, capsule separation was disabled. The jettison of the escape rocket activated the capsule parachute recovery system. Since the altitude was below 10,000 feet, this system was triggered by its atmospheric pressure sensors and followed its usual sequence, with the drogue chute deploying first, followed by the main parachute. But because the main parachute was not supporting the capsule's weight, the parachute system did not detect any load on this chute, so it acted as if the chute had failed and deployed the reserve parachute. Since the Redstone's automatic in-flight abort sensing system was running in open-loop mode, the engine shutdown did not trigger an abort. However, the system did report an abort condition, so it did function properly. To prevent a failure like Mercury Redstone 1 from happening again, subsequent Mercury Redstones added a grounding strap about 12 inches long to electrically connect the rocket to the launch pad. This strap was designed to separate from the rocket well after all other electrical connections to the ground had been severed. The Redstone had some minor damage from falling back on the pad, but it could still be used after refurbishment. So it was returned to Marshall Space Flight Center in Huntsville, Alabama. As it happens, the booster was never reused and is now on display at Marshall. A new test flight was scheduled, this one called MR-1A, which stands for Mercury Redstone 1A. The flight would use a new Redstone booster and the same Mercury spacecraft. Here's a clip of how NASA described the 4-inch flight.
The Redstone engine fired, then shut down almost immediately. The escape tower fired. The antenna canister lid opened, the drogue chute popped, followed by the main chute, and then the reserve parachute. When the spacecraft received the engine shutdown signal, it began to do exactly what it was supposed to do. In response to the signals received, the craft functioned properly. Both the escape rocket and the parachute recovery system went through the normal sequence of action. A careful examination of telemetry data and the booster itself showed the premature engine shutdown to be caused by a relatively simple fault in a piece of ground support equipment. During the launch attempt, the booster was damaged. It was removed from the pad and shipped back to the Marshall Space Flight Center to be repaired.
Mercury Redstone 1A was launched on December 19, 1960. It was a repeat of the earlier Mercury Redstone 1 with the same objectives. This time the launch went well, and with the exception that the launch vehicle cutoff velocity was slightly higher than normal, all flight sequences were satisfactory. All measured abort parameters remained below the limits, and the abort system functioned as expected. Tower separation, spacecraft turnaround, retrofire, retro package jettison, and landing systems all worked correctly. The spacecraft achieved a maximum altitude of 210 kilometers and a maximum velocity of just under 8,000 kilometers per hour. The spacecraft traveled downrange of the launch facility 375 kilometers in a flight that lasted 15 minutes and 45 seconds. About 15 minutes after landing in the Atlantic Ocean, the recovery helicopter picked up the capsule. Here's the 1960 newsreel of the flight.
At Cape Canaveral, the 7 United States Project Mercury astronauts are among the observers at the firing of a Redstone rocket carrying an unmanned space capsule. The capsule, called the MR-1A, is an exact replica of what will be America's first man-in-space capsule. After the flawless launching, the carrier rocket heads down the Atlantic firing range until it burns out and separates from the capsule, which travels 135 miles further out into space before returning to Earth. The re-entry is as flawless as the launching. It's the first wholly successful test in the Project Mercury series. The entire sequence in space took 16 minutes from blastoff. Scientists reported that everything went exactly as planned. The capsule, which carried some of the most complex instruments involved in any United States space shot to date, returned in fine shape. Good news for the astronauts, one of whom will stake his life on its performance sometime in 1961.
Mercury Redstone 2, MR2, was intended to be the penultimate test flight of the Mercury Redstone launch vehicle prior to the first manned mission. MR2 contained 6 new systems that had not been on previous flights. 1. An environmental control system. 2. An altitude stabilization control system. 3. Live retro rockets. 4. A voice communication system. 5. An active abort sensing system. And 6. A pneumatic landing bag. It also contained a live chimpanzee test subject. Chimpanzees were used because their organ and skeletal structures are similar to humans, and they can be trained. On January 2, 1961, 6 chimpanzees and 20 medical specialists and animal handlers from Holloman Air Force Base, New Mexico, where the chimps lived and were trained, were moved into quarters behind Hangar S at Cape Canaveral, Florida. All 6 chimps were trained in Mercury simulators for 3 weeks. The day before the flight, 2 chimps were chosen for the mission. 1 primary, Ham, and 1 backup, Minnie. The competition between Ham and Minnie was fierce, but Ham was full of energy and, in general, a fun-loving kind of guy. So he was selected for the mission. What is not commonly known is a secret vote was taken among the other chimps, and Ham was unanimously selected by his peers to fly this mission. Just kidding. The chimps were smart, but they weren't quite smart enough to take a vote. Ham hailed from Cameroon, Africa. His birth name was Chang. He was purchased by the U.S. Air Force on July 9, 1959. He was 3 years, 8 months old at the launch. Ham was named in honor of the Holloman Aerospace Medical Center, HAM. On January 31, 1961, Ham was placed in his flight compartment and inserted into the Mercury capsule in preparation for launch. Then the countdown was delayed almost 4 hours because of an electrical problem. Finally, the countdown was resumed and MR2 was launched, and then things started to go wrong. 1 minute after the launch, the computers reported the flight path angle was at least 1 degree too high and rising. At 2 minutes, the computer predicted Ham would be subject to a 17G acceleration. At 2 minutes 17 seconds into the flight, the liquid oxygen supply was depleted. The abort system sensed a change in engine chamber pressure when the liquid oxygen supply was depleted and fired the launch escape system. The abort signaled a mayday message to the recovery forces. At 2 minutes and 18 seconds into the flight, the cabin pressure dropped from 5.5 to 1 psi. Fortunately, Ham was safe in his own spacesuit and did not suffer any ill effects from the loss of cabin pressure. His spacesuit pressure remained normal and suit temperature stayed well within the 60 to 80 degrees Fahrenheit optimum range. The high flight angle and the early abort caused the velocity of the spacecraft to reach over 1,000 feet per second higher than planned. The retro rocket had been jettisoned during the abort and therefore could not be used to slow down the spacecraft. As a result, the capsule overshot the planned landing area by 209 kilometers and reached an apogee of 253 kilometers instead of the 185 kilometers that was planned. Ham's trip took 2 minutes and 24 seconds longer than intended, with a total flight time of 16 minutes and 39 seconds. Ham's peak G-load during re-entry was 14.7, almost 3 Gs more than planned. But Ham's performance during the flight was excellent, with reaction times for his required task of lever pulling roughly equal to his pre-flight test despite his vehicle's performance problems. When MR2 splashed down, no ships had yet reached the vicinity, having landed some 100 kilometers from the nearest recovery ship, the destroyer USS Ellison. A P-2V search plane located the capsule about 27 minutes after splashdown. Helicopters were dispatched from the USS Donner, as at least 2 additional hours were required for the Ellison to arrive. Although, when the search plane had located the capsule, it was still floating upright, by the time the helicopters arrived, they found MR2 on its side and taking on water. It was determined that the beryllium heat shield had skipped on the water on impact, bouncing against the capsule bottom and puncturing 2 holes in the titanium pressure bulkhead. In addition, the plastic landing bag was worn badly, resulting in the heat shield being torn free. Water entering the cabin became worse when the capsule capsized, allowing more water to enter via the open cabin pressure valve. When the helicopter latched onto the capsule, the pilot estimated an extra load of nearly 800 pounds due to the seawater. Ham was returned safely to the USS Donner, apparently no worse for wear. Sometime later, after his flight, Ham was shown the spacecraft, and it was visibly apparent he had no further interest in cooperating with the space program. And with that, Ham retired from the space program. He moved to the National Zoo in Washington, D.C. for 17 years, and then in 1981, he moved to a zoo in North Carolina to live with a colony of other chimps. He died on January 19, 1983, at the age of 26. Ham is buried at the New Mexico Museum of Space History in Alamogordo, New Mexico. He was one of the many animals in space. Now here's a newsreel made after the flight. The newsreel barely mentions all the problems that occurred on this flight.
The firing is a success. But what of little Ham? Has he survived the tremendous shock of takeoff? Is he alive? Yes, remarkable motion pictures made in flight show Ham, bottom screen, playing the game of levers and lights just as he has been trained to do. Reaching an altitude of 35,000 feet, the rocket's vapor trail starts to scar the sky. Here in animation, capsule and rocket separate 2.5 minutes after launch. Here, the same action captured in truly amazing films. The capsule spins over. Its heat shield, designed to withstand temperatures of 3,000 degrees Fahrenheit, is in a forward position. Ham is weightless in a world of zero gravity and will be for 5 full minutes. He appears not to be affected at all as he carries out his assigned tasks. Now the capsule's tiny control rockets turn it down toward Earth after reaching a height of 155 miles. A small parachute opens 4 miles above the Earth to cut the speed of descent. At 2 miles, a larger parachute opens. Beneath the capsule, a landing bag is inflated to cushion the final landing impact. When the capsule hits the water, the parachute is released, and a sea-marking dye spreads out to aid in the recovery. 18 minutes after launching, the space capsule with Ham inside is bobbing in the waters of the Atlantic Ocean, 420 miles from Cape Canaveral. It is plucked from the water by a helicopter and airlifted toward a recovery ship that is waiting nearby. Although the chimpanzee's actual space flight lasted only 18 minutes, the capsule overshot its mark and thus delayed the recovery. And so it is 3 hours before the chamber is gently lowered onto the deck of the landing ship Donner. The question on everyone's mind is, how did he take it? And implied in that question is still another. How in the future will man take it? And so, anxiously, impatiently, hopefully, technicians and medical personnel work feverishly to free the amazing creature who has just completed this giant leap into space. They can see him now, but still the plastic cover of the chamber must be removed. Ham has done it. He is safe and well, a hero of space, happy to be back among friends. Completely contented chimp, he has moved man closer than ever before to his age-old dream of traveling the heavens.
Obviously, that news report was a little too optimistic. With all the malfunctions during the flight, the Mercury Redstone proved it was still not ready for human flight. The first manned flight that was supposed to be next had to be postponed pending a final booster development flight called Mercury Redstone BD. The Mercury Redstone booster development flight was the last unmanned Mercury Redstone mission. The cause of previous Redstone rocket over-accelerations was determined to be a servo valve that did not properly regulate the flow of hydrogen peroxide to the steam generator. This, in turn, overpowered the fuel pumps. To fix the problem, the thrust regulator and velocity integrator were modified on the Mercury Redstone BD and later Mercury Redstone rockets to prevent them from exceeding the speed limit again. Another problem encountered in previous Mercury Redstone flights were harmonic vibrations induced by aerodynamic stress in the topmost section of the elongated Redstone. To fix this problem, 4 stiffeners were added to the ballast section and 210 pounds of insulation were added to the inner skin of the upper part of the Mercury Redstone instrument compartment. The Mercury Redstone BD mission used a boilerplate Mercury spacecraft with an inert escape rocket. The spacecraft also did not have a retro package or booster separation rockets. MRBD was successfully launched on March 24, 1961, about 19 days before Vostok 1. The launch vehicle achieved a maximum velocity of about 8,200 kilometers per hour and an altitude of 180 kilometers. The capsule traveled nearly 500 kilometers downrange for a flight that lasted 8 minutes and 23 seconds. All test objectives of the flight were met. As a result, the launch vehicle was approved for the planned manned suborbital flights. At first glance, it seems the U.S. missed another opportunity to be first. If MR2, which was launched on January 31st of 1961, had been a success, it was possible that the U.S. could have been first to put a man into space as early as March 24th, 19 days before the Soviets did on April 12th. But that's not the way it happened. In any case, Mercury Redstone was ready. The U.S. had fixed their little problems and were ready to light that candle. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.